optical grain is better. That's why turn green for a while. You wait for a little while. Usually, what you do is you click here, you put it down in the pocket. Okay, that's it. Okay, thank you. Yeah. Okay, good morning. So before the class, I have a few announcements, okay, to make sure you know what's going on. The first thing is there are still students sending me emails about changing the credits. Some want to change from 4 to 3. Some want to change from 3 to 4. Okay. So any change, because this is the third week already, the university basically says for the first 2 weeks, you just send me emails. I send it to registration desk in the academic office. They will do it for you. Okay. But starting from week 3, any change, we need a formal course change form. Okay. And the change form, you need to get instructor's signature. Essentially, is you drop one session, add another session. Okay. For example, if you want to drop, say, 4, like I assume it's you originally signed as a P4. Okay. Then you will write down, you drop P4 of CS412. You add P3. Okay. Remember the number. You drop P4, you add P3. Okay. You should not add to A3 because A3 is video only. Originally, you were on the in the classroom. Then you add A3, become you are out of the classroom. Okay. Which is not to your benefit. Okay. So from P4 to P3, you write it down. One is drop, one is add. You need my signatures. I need to sign both, essentially, drop and add. So without my signature, they're not going to change the course. Okay. Question? That's in the last 2 weeks. But starting week 3, you'll need my signature. That's based on their message. That means if you did it last Friday or before, everything was fine. But starting this week, you will need my signature. They're not going to process it without my signature. That's a message I got from them. Okay. And from 3 to 4, there's a little trick. Okay. 3, if you originally register us in class session. That means P3. You write down, you drop P3, you add to P4. If you were on A3, A3 means video only one, okay? There's no A4 open yet. So if you want to change from A3, you will change to P4. Okay. P4 means in class. That means originally you were video only, but you want to take full credits. You actually in class, you have priority to be in the classroom. Okay. So remember, the session is a little different. If you were in the A3, you want to get into 4, you change to P4. You get my signature. You still can get into the P4. Okay. P4 originally was completely booked, but after we give the assignment, we do have a few students who dropped the course. So we do have a few room. Okay. So some people can get in. But that's the reason if you change from A3 or P3, you all can get into P4. Okay. The same thing as my second notice is if you still want to join the course, suppose you are on the waiting list, you want to join the course, you discuss with me. There's a good possibility you may be able to join because we do have a few students drop the course after the first assignment. So we do have a few rooms. As long as a small number, we may be able to handle it. Okay. But you needed a course change form, okay, adding the course. Okay. So the third thing is about homework assignment 1. Okay. Remember, we pushed this assignment out in the late August. So the due date, I think, is the 15th. 15th means 11:59 on 15th. You must hand in. Okay, there's, based on TA, discussed with me, they say they will not take late assignment. Okay, so you need to finish on time. If you have any trouble getting to online on the campus, you need to let me know immediately. Okay, we try to handle it case by case. But based on my information, almost all the students, they do not complain. They are working on it. Instead of complaining, they cannot get in. If you cannot get in, you have to see me as soon as possible today. Okay. So that's about a homework 1. Okay. If you got a problem, you need to consult TA or you need to seek help. You can either finding TA office hours or find me right after class, or you send some information on Piazza. Somebody may help you to solve a particular problem. Okay. Piazza is a good help. Before you raise question, you trace the history. Probably your question already been handled by other discussions. You read the history, you probably get a better idea. Then you probably can handle it by yourself. Okay. For particular help, not exactly the question answer, you can discuss with other students in class as well. Okay. That means the general help you can get from the classmates. But you should not expect the classmates will tell you the concrete answer of any question. Okay. You have to do it by yourself. That clear? Okay. So for the next lecture, Dr. Meng Jiang will teach. He is a research scientist. He actually has been with us for a year. Okay. Because I will be in Denver to attend a conference. I'm organizing a session, so I could not fly back on time. He will be teaching next lecture, Tuesday lecture. I will still be teaching Thursday lecture next week. Okay. So that's the announcement. Hopefully, everybody got this. You can download this slides again. You will find this assignment in the set of slides. So you watch out, especially for anybody want to change course. I will not wish to receive more emails. This morning I still receive emails. I told the student, I already announced in Piazza yesterday. You have to get signature from me instead of just trying to give me your ID and ask me to change it from the secretary. Okay. So last time we discussed about data reduction and data transformation. We introduced some interesting techniques like a wavelet transform or lots of different compression methods. Okay. This time we're going to discuss a very last one, but an important one called dimensionality reduction. Okay. What is dimensionality? Okay. Usually dimensionality has many, many names. Okay. Depends on which research domain, which discipline you're working in. Okay. For example, if you go to statistics, likely in statistics they will call variables instead of dimensions. Okay. They may say select or reduce number of variables. Okay. But if you go to machine learning, maybe they are talking about features. They say select the features or reduce features or doing some kind of feature transformation. Of course, many nowadays machine learning literature they also call dimensions. But you go to database domain, likely you will say attributes, right? They say, oh, you got a relation, you got many, many attributes, you want to reduce number of attributes. Essentially, they are talking almost the same thing. Okay. Scientifically, most people call this dimensionality reduction. Okay. Why we want to reduce number of dimensions? Okay. The first important thing is, in any data analysis, only some dimensions are critical. Okay. Just thinking about this. Suppose I want to give students awards. Okay. Some fields or some attributes of variables actually is irrelevant. For example, your phone number. I don't want to give you a award because you have certain phone number, okay, or social security number, or student ID. Okay. Those are irrelevant. Or even your date of birth or your home address. Actually, I do not give you because you live in Illinois, right? So that's obvious. So that means there are something should be excluded in your analysis, but the data analysis package may not know it. You probably want to analyze. For example, you give me some training data. So those people getting awards, these people did not. Maybe I will have a way to figure out the telephone number is irrelevant, the social security number is irrelevant. I actually doing some kind of training, I find some dimensions are more useful. Okay. So that's the reason we want to do dimensionality reduction. Actually, most data analysis, you got data, you get many, many dimensions. Okay. Some very long, some short. Just give you a simple example. If you analyze text documents, they do not know what is dimension. They treat every word or every phrase as a dimension. They give you the whole document, which is thousands of dimensions. Right? You must have a way to reduce them. Otherwise, you get thousands of words, you do not know which word is critical. Because in many cases, many words getting together is important. Right? So that's the reason we want to do it, but it's not easy to do. Why is it not easy to do? The first thing is, once you get a very high dimension, you get a curse of dimensionality problem. What is curse of dimensionality? The first thing is, once you get a very high dimension, originally dense data, once you map into high dimension space, it may become extremely sparse. Why it became extremely sparse? I believe when you were young, you probably watched the sky, the night sky, you see lots of stars. You find some stars are very close. There are so many. You see this is the Milky Way. That's so many stars. You think they are very close. But you ask any astronomer, okay, they probably say, no, you look very close. Actually, they are very, very far apart. Maybe they are, billions of miles away. But, why you see so close? Because you did dimensionality reduction. Originally, the star is in the 3D space, right? But if you watch the night sky, actually map them into a 2D space, right? If they are in the same corner, okay? They are very far apart, but once you get 2D, the two stars may become very close, right? So, but once you stretch them into multi-dimension space, they become sparser. Right? That's obvious, right? That's only 3D. You think of a star in 3D. But in your data space, actually you better get a very high D. Once you get a very high D, the data become extremely sparse. Okay. You try to compute their distance, or doing clustering or doing any kind of analysis, you get difficulty. Okay. That's the first problem. Okay. Another thing is once it becomes sparse, you try to do analysis, you even try to work out the meaning is not easy. Remember, we work on a meaning like Euclidean space, Manhattan distance, and all these distances. 2D, 3D, you calculate distance become very easy. You just use, for example, Euclidean distance. You get a 2D space. It's very easy to calculate whether they are far or they are close, right? But what about they are sitting in a completely different dimensions? It becomes not even comparable, right? You are in this dimension, we're in that dimension, we're not comparable, okay? So in that sense, try to do analysis becomes really hard in a very high dimension. The third problem is once you get dimension, get a very high dimension, the space you want to analyze some subspace. How many subspaces you will have? You're thinking about it, suppose you got 10 dimensions. Okay. Actually, you want to analyze all the different combinations, you get 2 to the power of 10 combinations. You get 100 dimensions, no computer can handle it. Right? You think about all the possible dimensions, it's 2 to the power of 100. Who can handle it? Right? So that's the reason you have to do some reduction. Otherwise, you try to compute all the subspaces, you get exponential number. Right? So that means we have to do some dimensionality reduction in order to really analyze any kind of data in a meaningful way. Okay. Then, how do we do dimensionality reduction is this part. This one, we are going to use a few slides to explain it. Okay. But first I should say is, if you want to reduce the number of dimensions, you actually get a lot of advantage. The first problem is you try to avoid the curse of dimensionality. Because you get a high dimension, you just cannot analyze them, right? And also, in many cases, you chop something which is irrelevant. It only help you in analysis. Just thinking about this, okay? If you analyze student word, you chop out, say, birth date, or a student number, or a phone number, you chop them, it only help you, right? Because those things have nothing to do. Why you do not throw them away? So the third one, of course, you reduce the time and the computation time as well, and it's easier to see because you map them in 2D, 3D. It's much easier to watch them, right? Now we will say how we do dimensionality reduction. This actually is a big topic. If you go down to some bookstore, you'll probably see the dimensionality reduction itself could be a very thick book. There's so many tricks you can play. Of course, we are doing data processing chapter. We are not going to give you very detail on everything. But in general, we can say dimensionality reduction have two general ways. One we call feature selection. Another we call feature extraction or some kind of transformation. Okay. What is feature selection? Feature selection means there are so many dimensions. Only some of them will be useful. You select those things. For example, if you want to give a student a word, suppose the student GPA or those critical courses are very important. Okay. Actually, when we do like a graduate student recruiting, we first look at your GPA, then we actually look at some key courses. For example, we know this complexity of the algorithms is very tricky. You probably look at those scores, what grade you got. Or some particular math or optimization or something is very needed. We probably look at those courses, grades. But if you get a B in history or in some philosophy or something, we probably say, that's fine, we forget this. Okay. So that's not just the number of the score is 3.9 or 3.8 is a decisive factor. That means we actually know how to select features. We definitely do not look at your phone number, right? So that's the case. Feature selection is only pick a subset. You pay more attention, put more weights on it. Okay. What is feature extraction? Some people call this as a feature transformation or, The extraction essentially is saying the feature, none of the features is really great. I actually want to combine them in some way. I transform them into lower dimension space. Okay. There are many tricks to do this. One we are going to show you is called PCA, Principal Component Analysis. There are many others. Okay. This feature transformation or feature extraction is very important, but it's a little tricky. You need to do a little math to get multiple features transformed into a smaller number. Okay. Then I'm going to give you a few methods here. One we were introduced, but it's still not introduced in a very detailed way, called Principal Component Analysis. Some people simply call it PCA. Okay. Another one we are going to introduce is some kind of feature supervised method or nonlinear method. That means not using equation computation. But we are going to introduce one is how to do subset selection, feature selection. Another is how to create some new features, critical features. Okay. Now, I first introduce you called PCA. How many people know PCA? We got it almost half. That's not bad. Okay. So if you go to some statistic course or some, even a lot of signal processing or pattern recognition courses, they take PCA quite seriously. Okay. What is this? Basically, this is some kind of statistic algorithm. You can think in this way. You actually convert a higher dimension space. Usually, you probably using the space, you represent them like a covariance matrix or something. Okay? Then you try to compute finding some correlated variables. But that variable may not be, in most cases, is not the original variable. You actually change them into some new variables. The variable usually is a few, orthogonal new dimensions. Okay? And these new dimensions, you map them there, you got several most important dimensions extract out. These dimensions, we call them as a principal component. Okay. So you get a principal components, just a few. You map original high dimension space into low dimension, mutually independent, we call orthogonal principal components. This process is principal component analysis. That's called PCA. Okay. That means the original high dimension space, you almost completely drop them. But you use a small number of principal components to replace them. Okay. That's the idea. Okay. Then I give you a simple example. Suppose you got, even we do a simple analysis, anybody if you study physics. Okay. Suppose you get a string, the string attached to some kind of ball, okay, like a iron ball or something heavy. Okay. And the physics teacher will say, if I drag this ball down, okay, then I release it, you'll see how it moves. And anybody in high school, you probably learned this already. You know the string based on elastic, and there's a force. One is the string itself has a force, another is the earth has gravity. You drag it down. So once you release, you stretch it to release it, the string started bouncing back and forth in one dimension space, right? Suppose you're handing it, you just pull it down, not swing it in that way. You pull it down, then they are going to go up and down in single dimension space. Okay. That means if you really watch its movement, 1D will be good enough. But suppose you do not know this. You got 3 cameras in different ways. Okay, the 3 camera, because the camera may not be vertical or horizontal, they could be in different angles. Then, if you look at the camera ABC, you'll find that the movement is rather complicated. Okay, 3D space, you get 3 cameras, you get a very complicated movements. You will say, wow, this is really complicated. You probably want to see. There are 3 variables. Everybody is moving in some very strange or some different ways. But actually, if you ask any physics teacher, they say it's very simple. You just watch 1D. Okay. But suppose you got 3 cameras, you get all the movements registered. You got 3D space, you get very complicated movements. You did not catch the essence. The essence is 1D. Okay. How the mathematical routine can do this? Mathematical routine is supposed to say, I do not know what it is. I got your ABC3 cameras. They all move in complicated ways. But actually, I may analyze, have some magic finally find, actually just if I reduce them into 1D. Okay. It's so straightforward, I can work out a nice, simple, clean equation, right? So originally you think it's so complicated, you get a very clean equation. Actually, if you're thinking about human history, originally humans watched the sky movements. They originally thinking the Earth was stable, okay, it was never changing. Everything was turning, okay. The sun was turning like every 24 hours, like turning one round, okay. And the planets are turning in a rather complicated way. They actually try to work out equations, okay. That time you need a lot of math to do a lot of very complicated equations, try to predict these 2 planets someday will line up, or moon and sun may line up. It's very complicated, right? That means you are not doing this principal component analysis. You did not catch the essence. You just watch everybody moving in a strange way. But, you know, in 2007, I went to University of Warsaw to have a conference. Actually, in front of their campus, there's a huge statue of Nicolaus Copernicus. Okay. He was the first one saying, if I take not Earth the center, but I take sun as the center, actually, I will find all those things moving, including Earth, including moon, including all the planets. They move in a very simple equation. Okay, some equation like, you know, like a quadratic equation, like something almost like an ellipse or a round ball, or like a just circle. I actually can compute it in a rather simple way. Okay. He was doing some transformation. Just transform into sun as a center, actually he got a much clean answer. So if you think this is, you find a principal component. Okay? Sun is the center, not Earth the center. Okay? So there are many simple ways you can transform them, right? Of course, Nicolaus Copernicus was the hero in Poland. That's why their top university put a so huge statue there, right? So principal component analysis means you want to transform very complicated thing into a simple thing. How do we transform this? They have a very nice procedure. Okay? The procedure is you try to find eigenvectors of covariance matrix. Okay. Remember last time I gave you the covariance matrix? The covariance matrix, you actually can compute eigenvectors. Okay. But I'm not going to teach you there because otherwise I branch down to almost another course. I just tell you, you know, there's a very nice thing. You want to know more? I just outline here, but to learn more, definitely I would recommend you to go to a statistics class or some other class to learn it. They probably spend 1 or 2 weeks discussing this. Right? So the principal component analysis method basically saying you get a capital N, a lot of data points, data vectors. Each one has a small n dimension, but these small n is still many. Okay, this could be 10 dimensions or something, right? But you try to find the k orthogonal vectors or principal components. It could be a very small number, 1, 2, 3. Those very small number. You want to reduce your 10 or 20 dimensions into, say, 3 dimensions. Okay, that means this k is the principal components you want to get. Okay, and you want to, you know, represent all the tricks or movements using these 3 components. Like here, you can see there are so many things around. You finally find if you got you know, these 2D vectors, you probably can describe in a rather simple equations. Okay. picture I actually got from Wikipedia PCA entry. If you type Wikipedia principal component analysis, you get the same picture. Okay. Then what they do, they first normalize the input data. That means they try to normalize, in many cases, normalize all these things, different dimensions, of 0 to 1. Okay, you normalize into this. Then you compute this K orthonormal unit vectors. Okay, this is the principal components. And how do you compute them? Actually, this is exactly, you use covariance matrix to compute their eigenvectors. Okay, but I will not give you the detail. You have to check the statistics course, or you check maybe some Coursera course, it will give you more details. Okay. Then every vector, you will map them. That means every data point, you can map them into a linear combination of this K principal components. Okay. That means every vector originally, you can map them in just, suppose you get a 3D, or you think about it for the string, you just get a 1D. You just map them down to this 1D. Then you will see the moments, right? So the principal components usually sorted in the order of decreasing significance or strengths. This is similar to Fourier transform. If you think of the Fourier transform, you got the first component. You get most of the energy in the first component. Then you get second one, third one. Okay, the later one, you almost can ignore them because they have very little value. This is a similar thing. Okay, that means the components are sorted, and the things in the other components you find is pretty weak. That means you get a first, second, third. The importance decreasing, you get a later one, you become less important, you become pretty weak. And those weak ones, you can chop them off. Okay, that's the reason you reduce the number of dimensions into very small number of dimensions. Okay. For example, you use this camera, you know the string is moving just vertically. Okay. The other dimension, you finally find their variance almost nothing. They do not really go in the other dimensions because you finally find that this vertical one is a rare thing. All the other, you tier your camera, those tier things you finally find is not so essential, you just drop them. Okay. Finally, you find only 1D, play the real equation, right? So that's a principal component analysis. Okay. That one, I will not give you the detail, just say, if you want to do it, you know we already learned this covariance matrices, and you play with that. You do the transformation, finally compute the eigenvector. Now we get into another trick, is attribute subset selection. That means you got many, many attributes. You get many, many features. You only want to select a few essential ones. This one different from the principal component because the principal component is transformation. You throw away the previous features. You transform into principal components. Here you don't transform them. You just check which one is important. But how do you check them? There are two important things you want to check. One is redundant attributes. Another one is irrelevant attributes. What is redundant attributes? Okay. Suppose you got fields in your own record. One is age, one is a birth date, or birth year or something. Birth date, you get a day and a year, right? You finally find that actually for age and birth date, you probably only need one instead of using both because they are strongly co-relevant, right? One actually can derive the other or almost derive the other. Why you want to keep both? Why you analyze, you put both of them in? Because they are redundant, right? So you know they are redundant, you actually can chop one, you preserve a better one. Maybe preserve your birth year is better one because the age actually depends on different years. They keep changing, right? You want to compare them. Sometimes it's a little hard. For example, you go to web, you check Obama's age. Some people say 46, some people say 53. You get confused, what's the real one? Actually, if you check birth year, there's only one. And you say 46, it depends. That's the year he first became president, right? So, now the age is changing, right? So that's the reason you want to chop redundant. Even you think about it, you analyze, give student awards. You get a GPA. GPA is an aggregation of many courses. Okay, you go to each course, you have homeworks, you have, like a midterm finals. Why keep so many numbers? Right? You probably just use GPA, or some people say, I want to get a critical class GPA as well, like a major GPA or CS GPA or something. So you get this. So that means you chop the others. That means you try to remove duplicated attributes. Okay. For example, like last time I said, you go to restaurants, you get a bill, and you also get a tip. Okay. But it's only one is important. Probably just keep the bill and throw away the tip because, they are correlated. Irrelevant attributes means something you really don't want to put in your analysis. For example, like you want to give a word, you put student ID in or student number in. No matter what, you want to chop them. Okay? So those are the means you need to do relevance analysis. You find irrelevant one. You comfortably not include them in your analysis. Okay? Then how do you really do the search? Because you get so many attributes. Okay. You may have some kind of training things or some kind of training thing means, suppose I already know, I look at the previous record how people select the students for awards. Okay. I got some training data. Now it's this year. I probably want to use this idea to chop out some attributes, preserve some other ones. Okay. So how we do this? Suppose you get many possible combinations for D attributes. That means you get D, you have 2 to the power D possibilities to select the subsets. Right? Suppose you have 10 attributes, you can say select 1, but you may say, oh, 1 is not enough, select 2. How I can select 2 or select 3, select 4? You have 2 to the power D possibility. Right? Well, with that many possibilities, you don't want to, even you want to search, you judge everyone, it's so complicated. So you want to have a heuristic attribute selection method. And how do you select it? Okay. Of course, you can say, you can first select which single attribute is useful. Okay. That's usually, you can take a single attribute to check their relevance. For example, if you want to get awards, you check student ID, whether it's anything to do with awards. You finally find there's nothing to do. You can chop it. Okay. That's take the best single attribute. You can do single attribute analysis. But in many cases, something is 2 getting together, 3 getting together, really important. 1 you actually cannot even tell. Right? If, for example, you think about even when you buy a land, you just cannot look at 1 land. So you need to look at 2. 2 getting together, the land area probably becomes more useful rather than just look at 1 dimension, right? So that means sometimes you need to do combined analysis. So how do you do this? Actually, there are several ways to do. One they call best stepwise feature selection. That means you pick the best feature first, then you try to pick another feature, then pick another one. So that's the best first. You pick the highest one, then you pick the second one, pick the third one. Another way is you try to eliminate. That means I do not know which one is important, but I know this one definitely is nothing to do with it. For example, if you say phone number is definitely not related to words, so you can easily say, first chop up phone number, then chop up maybe like student ID. But maybe the birth year is still useful, or I probably put it there at this point. Later, may finally find the birth year has nothing to do, I can chop it. But maybe it's useful because I find some younger ones may have a chance to get awards higher, right? You can keep it. That means you do stepwise attribute elimination. You pick up the worst one, you chop it first. Then you chop the second worst. Okay? Or you combine selection and elimination. Combine means you evaluate this attribute, you say this is really bad, you chop it. This is maybe good, or this is really good, I pick it. So when you do it, you do one evaluation, you make two decisions, okay, or actually three. There's one, I chop it, one, I select it, another one is wait, I have to look at others. I decide whether I want to include you or not. Okay. So there are many other ways. Another one called optimal brand and bound search. That typically is kind of heuristic search. You want to eliminate them, then later you find, oh, I may get something back. You actually try to find the best path to go. So this is the attribute selection. Okay. Then another one is attribute creation. Okay. Creation is also useful. Sometimes you may find none of these attributes is really, really good. You probably want to generate a new one. Okay? So in that sense, you may create certain attributes. Some creation could be you do some complicated mass transformation. You create something. You can actually thinking about it. Even you do principal component analysis, you create some new attributes. Okay? There are many ways to create. One is you may have some domain-specific analysis. You finally find it. For example, they originally just give you a birth year. Maybe finally you want to say this is not that good. You transform into age. Then you create an age group. You say this is young, this is middle age, this is old. You create a new dimension. And for medical doctors, sometimes you do want to have such analysis. You simplify things. And constructing attributes in many ways, they are actually later in the classification chapter, okay, in the later course. I actually will give you some classification methods. They combine several attributes and do some transformation, create new features, which is better than any single ones. Okay, they have some systematic techniques. So this is called attribute construction. So I just summarize. I just say for data pre-processing, there are many tricks. We need to guarantee the data quality, to do data cleaning, data integration, data transformation. And we also see there are lots of tricks to do data reduction and transformation. And we finally discuss this dimensionality reduction. If you go to some other textbooks, some textbook put dimensionality reduction as a big chapter. Okay. Here we insert as just one section. Okay. So that simply says dimensionality has lots of tricks you can learn. Okay. So there are lots of textbooks or reference papers you can study. There are lots of softwares available as well. Okay. So here, the end of chapter, I give you one picture. Anybody can guess where it is? Yeah, this one is in Athens. If you go to Athens, you visit the Acropolis. Actually, along the way, they have one. This one, I think, is at least 3,000 years old. Okay. It's an amphitheater. Okay. Even now, you probably can see it's very clean because even now they use it for performance. Okay. But this parts of the things are very old. It's really like 3,000 years or more. But if you see the seats and the deck, it's pretty new. Okay, they keep it every day. But there are lots of things. You go there, it's amazing. It's like 1,100 years or BC or something. It's a very, very old thing. And it's really gigantic, really huge. Okay, so let's finish this. We get into a new chapter. Actually, we go a little quicker than we originally planned. But remember, later we will get some more difficult things. We can go a little slower. Now we get into chapter 4, data warehousing and online analytical processing. Okay. This one actually is another place in Athens. It's a very ancient, gigantic building. If you look at the person, you probably see it's so small. It's a really huge one. But most of them already gone. There are only a few giant pillars still standing there. But some, you can see this is lying down already, but it's gigantic. If you go down there, you see you are very small there. It simply says this several thousand years ago, you probably do not even know how they can construct these huge ones. At that time, there were no mechanical or the huge, giant machines, right? Even now, you move something, you use crane. You do not know the ancient people how they do it. Okay. Now we look at data warehouse. Okay. Actually, I assume most students played or learned database systems. Okay. What is database system? Actually, just a database system, they got quite a few tuning awards. I think a year ago, 2 years ago, Mike Stonebreaker got tuning awards. He was a professor in UC Berkeley that time when he did the database system as a starting one. Later, now he's a professor at MIT. What did he do for getting the tuning award? Okay. One important thing he did is he was one of the two major, pioneers working two newest, earliest relational database systems. One database system called System R was done by Jim Gray, who led IBM, that time not called Almaden Research Center, called IBM San Jose Lab. Okay. They led IBM San Jose to create the first relational database system called System R. Almost at the same time, UC Berkeley research group, led by Mike Stonebreaker, created another relational database system called Ingres. Okay. Ingres and the System R as the two newest relational database systems created in early 1970s. Okay. Then later, of course, nowadays you use Oracle, you use, like IBM still have a DB2, and you go to Microsoft, they have Microsoft SQL Server. They have gigantic team. Actually, if you look at the richest people in the world, actually the several top most richest people, they all have something to do with the relational database system. Like, Oracle, CEO, or like Microsoft, Bill Gates, and all these, they made a substantial share on their relational database systems. Why? Because when the computer came, the first useful thing is you want to manage data, any kinds of data. But of course, the first one to do is on reasonably structured data, like those records. Okay. To manage the records, no matter for factories, for companies, for universities, for governments, for anywhere, okay, they need an automated system. They don't want everybody spend millions or billions of dollars to get a very complicated system everybody develop on their own, maintain on their own. They want to automate it. And the relational database system is the first one which is domain independent. Okay. You work out the system, you do not even know your customer is a bank or is a university or a government or a company. But they all work. Okay. You put it in, they give you nice query optimization, nice security, and concurrency control, transaction management, everything. Okay. That's the big revolution for computer science. Okay. That's one reason, actually, Mike Stonebreaker also got both Jim Gray and Mike Stonebreaker got a Turing Award. Actually, I think in database field, there were total 4 Turing Awards in database system. One is Brahman. He actually worked out the first network database system. It's a little better, but it's not a relational. You still have to write a lot of code, adjust the pointers. He got it in 1970s. Okay. Then E.F. Cott, who was a mathematician. he was at IBM lab research. He was the first one proposed relational model. Okay. That means he did not really do the system work, but say for management data using these simple tables. And you can do join, you can do selection, you can do normalization. It will work. Okay. And he was the first one propose this picture. Okay. When he proposed this picture, even a lot of database people, a lot of computer science did not even believe this can be done. They think this is mathematicians, dream, science fiction. Okay. Because, join, all these are very expensive. And he actually lay out the framework, say this one should work, and it should be the future. And then later, both IBM and Berkeley, they all jump in. Okay. They made it work. That's the two newer Turing Award winner. Besides E.F. Codd, you get Jim Gray and get Mike Stoneberg. So that's 40 years, get 4 Turing Awards. Everyone, changed the history of the data management. But that's data management. But now people got lots of data. They are not satisfied with just doing query, doing transactions. They want to analyze data. Okay. How do you analyze data? A very important thing is you have to get data from long history, from different sources, all integrate them together, you can analyze them. Okay. That comes to a new concept called data warehouse. It's very interesting is the first several people proposed this data warehouse. One is Inman, another actually is Codd. Codd was the one who got a Turing Award. He proposed a relational table. After 20 years, he got Turing Award. After 20 years, he found if you want to analyze data, you have to integrate the data from many, many different sources, construct a data warehouse. And he proposed this data warehouse model. You can see the same person, right? But there's two major new things he actually thinks is very important. But what is data warehouse? Data warehouse means you want to separate from your operational database. Because the operational database, they store data in a different way. Okay, you want to separate them, but you want to integrate the data from many different sources, including historical data. Okay. They integrate into one data store, and you manage them in a different way because you want to manage them in an analytical way. That means you want to serve the data analysts. Okay. So that one, they call this one is data warehouse. And Inman, he was one of the early pioneers to propose this data warehouse. He identified 4 features. One called subject-oriented, another called integrated, the third one called time-variant, the fourth one called non-volatile collection data to support decision-making process. Okay. So these 4 keywords become the pillar, become the cornerstone to define and design a data warehouse. Now we will see how these 4, what they really mean, these 4 major, things called subject-oriented, integrated, time-variant, and non-volatile, what they really mean. Okay. But besides they call data warehouse, a lot of people also get a business called data warehousing. What is data warehousing? Data warehousing means you try to integrate data from multiple sources to design and construct and use the data warehouse. That whole thing they call data warehousing. Okay. I remember months ago, I went to my first employed place is Northwestern University. I was a professor there before I went to Canada. I found some older students because they got a reunion. We got one professor retirement, my friend. So I went down there, some older students I taught 30 years ago, okay, was there. I asked her, I said, what are you doing? She basically said, I was doing data warehousing for 20 years. Okay, so the data warehousing, you probably can see, is very useful, right? So data warehousing, actually one key point is subject-oriented. What is subject-oriented? If you go to a real company's database system, I actually remember many years ago, I went to that time I was in British Columbia in Canada. I went to BC Hydro, British Columbia, the energy company. Remember here we use nuclear energy or use some gas or something. British Columbia get gigantic mountains, huge mountains. They don't use oil, don't use coal, don't use anything but water. Okay, water is enough. Okay, they got huge water. It's more than enough to feed British Columbia and their industry and some part in Washington, okay, in the state of Washington. But they show me their database systems. I was amazed because they gave me about 150 relations. Each relation has 50 to 100 attributes. You know how big it is. They get a whole wall and with all the relation table. And each relation table, complicated one, they have another wall to show just that table. It's a very complicated, just schema, right? That means they are dealing with many, many subjects. You think about this. You go to Walmart, they are not just dealing with sales, right? They have the personnel, they have shipping, they have there's so many things they have to handle. They have many, many tables. To a certain extent, they have many subjects, right? Subject-oriented means you get a data warehouse, you're focusing on the analysis point of view. Okay? You deal with one subject at a time. You're not too ambitious. You're dealing with 100 subjects at the same time. It means you build one data cube, you handle one thing. For example, if it's sales, this is sales. The transportation or personnel is completely different. I don't care. I only care sales. I get a sales data warehouse or data model. Okay? So this is essentially called subject-oriented. That one, the general idea is you want to help decision-making. You want to analyze huge amount of data. You want to construct a simple and a concise view, not too complicated. Okay? That means anything not quite relevant to your decision-making process for this decision. For example, you say, I want to raise price, I want to reduce price. Or sales, which item I should pick up for sale. Okay? So they are looking for those things. They only handle one subject at a time. They exclude many, many other factors. Okay? That means you organize your sales may only care, for example, product and customer and sales, these three things put together. You construct one huge data cube or something. That's called subject-oriented. Okay. The second one, keywords, is integrated. What do you mean integrated? Integrate means if you want to analyze your business, you need to integrate many, many small data sets together. Just thinking about it. Suppose you are working for, say, Holiday Inn. Okay. The Holiday Inn has so many different locations, so many different states, and actually they have international business. You go to France or something, you find Holiday Inn as well. Right? So they are the same system. Okay. Then you try to integrate them. It's not that easy because you're just thinking about it, you give a hotel price. Here you give hotel price in US dollars. You go to France, they count as euro. You go to British, they actually use pound, right? And they have many different other things. For example, whether they cover breakfast or whether they cover some different kind of tax, different tax systems. So there are so many things. They are different, but you want to analyze them together because you may say, I want to open another hotel in France or close this one in some other places. So you want to do this, you need to think about a currency, tax, breakfast, or parking, everything included in your analysis. You need to integrate them. Have a same standard you can do analytical processing, right? So this data integration means time, location, heterogeneity, everything you have to integrate them. Data integration is a big problem. especially you probably see there are lots of company acquisition. I went to LinkedIn actually in my trip to Sigmod. They just disclosed the news they were purchased, acquired by Microsoft. So they actually are still doing their research in a very, very dynamic way. But company acquisition is a very complicated thing. The data integration is one of the complicated things in company acquisition because originally the definition, the name may have a similar name, definition is very different. The real contents is very different, right? That integration. The third one is time variant. What is time variant? Because you want to do analysis, you definitely want to look at the past. Right? Remember your current database system you got. This is your current. You do the transaction. You can check your current balance. Once you say, I withdraw $200, you check it again, the $200 is gone, right? The balance is reduced. So the relational database system, the nice thing is they only keep the current data, right? So everything you see is current. But from the analytical point of view, you have to know the whole history, right? So you have to know the whole history. How long the history you need depends on your scope of analysis. Some may go back to more than 10 years, right? They may check a credit history, loan history. There are many things, right? So that means operational database needs concurrency control right on the spot on your very current data. You and your brother, withdraw this account, even at the same time, they don't want to mess things up, right? They'll still get the right one. But for data warehouse, you need to integrate the long history. The history actually may be defined differently. Actually, it's very complicated. Resolution is different. The unit, even the same dollar, the value may be, the real value may be somewhat different because 20 years ago, you may only make half of the money. The $1 may worth more, right? So there are many things you need to handle. To do this analysis is not easy. This time variant means take time into consideration, right? The third one is non-volatile. Of course, you may say, oh, nowadays the disk is so huge. Anything is in the disk is not volatile, right? You get a relational database, your power shut down, the disk still preserves the most recent data. So it's non-volatile. But actually, this non-volatile means physically separate from the operational database. The reason is the operating database, things keep changing, okay? And the definition, there are many, for example, concurrency control, recovery. Actually, in data warehouse, you probably want to get rid of those things because you are not dealing with all the concurrent updates. Okay? And you do not have two transactions, one deposit money, one withdraw money. So you do not have those complexity, but you have to deal with a very long, time series or something. So the non-volatile means you separate from operational database, create your own independent data warehouse, integrate data, doing subject-oriented analysis, right? Then data warehouse, since you separate them, you integrate lots of data, you keep a very long history in detail, it's really huge, okay? That creates a different problem, for example, loading the data. Like your relational database, the loading data, only the very in the main memory is only very small portion. But in the data warehouse, when you want to analyze data, the data actually you want to see, maybe you analyze together with the last 10 years. So you cannot say everything is on the disk. Something must be in the main memory. So it's very different. That's why people actually use this table to say, if you want to analyze, you want to build a data warehouse, you will see these very different things between the two species. One is database system, they do OLTP. What is OLTP? OLTP means online transactional process. Transaction means the database. You do query, you can think of transaction, just no update. But you do the transaction withdraw, deposit money, create a new data, you are doing transaction process. All the query and transaction update belongs to OLTP. Okay. Relational database system, like Oracle, Microsoft SQL Server, they essentially doing OLTP. Okay. What is OLAP? OLAP is online analytical processing. Okay. Some people simply call this as OLAP. They say data warehouse is doing OLAP. OLAP means O is online analytical processing. Analytical processing means they want to analyze data, even the last 10 years data, even many, many different location data. They want to click the button to roll up and drill down almost instantly. That means last 10 years data, they want to clearly just draw a curve. Almost you click the curve is there. Okay, they don't want to say wait for another, coffee break, show a curve. They want to get a curve right away. Okay. So that means it involves many, many very different processing. For our data mining, we want to play with OLAP. That means we want to handle millions of records by clicking the button. It's there. Your mining result is there. Can we do this? Right. So you probably can see OLTP and OLAP. That means database system and data warehouse system are doing very different things. One is the user is different. The user may be just, for example, clerk, or even you withdraw money means any user. You go there, you can do it. But OLAP usually is by data analysis. You are doing roll up and drill down. You could be a business manager, like you're a CEO of Microsoft. You click the button, you want to see different sectors, how they change. Right. So those are the user difference. The function is different. The OLTP system is doing day-to-day operation because you are doing transaction, you are doing query, every day you are doing many such things. For example, you add a course or change a session. You actually doing OLTP in the relational database system, right? But doing decision support, you analyze many years data, many different branches, many products at the same time, you are doing OLAP. Okay. Database design, you probably can see one is application-oriented. You may have many tables, many factors. The other one is subject-oriented. And you are dealing with current, up-to-date, detailed relational table data. The other one is doing historical summarization, multi-dimension analysis. So the usage is different because many people are doing repetitive process, like you withdraw money. Actually, I got one interesting case was I went to, a year ago, in January, I went to Brazil, the Rio, the current, they just did the Olympics. Right? But it was a little dangerous place because there are lots of people, actually, there are some gangs. Right? I actually went down there. I did not realize I want to withdraw money. I withdrew the first time was successful. Okay, but I used up quickly. I want to withdraw again. Then the UIC credit union somehow, because I withdrew it from Brazil, okay, that's a very suspicious place, they blocked me. Okay, I tried it once or twice and 3 times. I tried more, they blocked me more. Actually, they freeze my account. So I actually just use a credit card to pay some bills. I do not care the exchange rate anymore. But when I came back, I talked to the credit union. They say, oh, in Rio it's quite dangerous. That's why we block you the transactions. Okay, you should understand it. The interesting thing was, after several months, there's some credit card company, actually the bank, that's the same bank and the credit card company, called me. Said, did you just do a transaction in Rio, in Brazil? I said, no. He said, that must be a false transaction. He said, within 20 minutes, there were 3 transactions withdraw money cash from your account. And then the money grew almost exponentially. The first one is like $20. They immediately jump up to like $100, then get another one like $200. They block it right away. They call me. And I say, no. They say, that is your cash company, your UIC, your cash card still with you? Yeah, I say it's still in my pocket. So how that happened? They say they have some tricks. You probably can see. Those, you do repetitive transaction. I tried it 3 times for the same bank machine. But somehow this bank machine was hacked. They actually got my credit card number, got a password. There must be maybe even something inside the bank. I do not really know. But you can see that's exactly these transactions. Because it's repetitive, they can simulate it. They can somehow make this card. They can insert into the bank, then they can actually get your password. They can get the money out. So that implies, actually, that's why data warehouse and database is different, because they need a security, they need a transaction management carefully. But data warehouse, they don't need that, because you are analyzing data. You're analyzing billions of data at the same time, right? So you probably can see the access is very different, okay? The unit of work is very different, because the OLTP just need very short transactions. The other one is doing very complex query. You roll up and drill down. You involve millions of records at the same time. Right? You can see that the record accessed for OLTP system may be single one, maybe only tens. The other one could be millions of records. You almost touch at the same time. Right? And the size is also different. The user, they say thousands. Actually, I probably should say millions, because anybody has a bank card, they are accessing the OLTP system, right? But the database size, you probably can see, usually for relational database, you are handling megabytes or gigabytes data. But for OLTP system, you are doing analysis. You are really doing terabytes or terabytes at the same time. That's why you can see you need a different system. That's OLTP or data warehouse system. It's a new, different system. Okay. For this, you probably can see we also say, because these two systems are so different, we already see the comparison. You need a separate system. The separate system is the data warehouse system, because the database system is tuned for OLTP transaction processing, right? You have a very fast indexing, accessing method. You have a concurrency control. You have a recovery. Many of these are not critical for data warehouse. For example, you probably don't need to have so high security on individual users, because they are not withdrawing money. They are doing analysis. And you do not need concurrency control, because barely you will have concurrent updates. Right, because you're not withdrawing deposit money to the same account same time. Okay. And the recovery is also less required, because the data, you just load the data. Okay. You don't update them. But you need to do complex OLAP queries. You need the summarization. You need a multi-dimensional analysis. That's a different thing. And if you use relational database system to do data warehouse, to do OLAP processing, what is the problem? One problem is missing data, because the database usually keep your current record. They do not doing your 10 years, last 10 years data. They roll to another disk or somewhere. They do not do this. The data could be missing. Another one is data may not be consolidated. Consolidated means you do a lot of aggregation. Later you are going to see, once we get into next lecture, you will see. There are many ways you have to summarize data. Okay. To summarize data, you think about Walmart people. Okay, Walmart, say, CEO or business manager. They want to analyze whether last month the diapers sold in Illinois versus Michigan, why they are so different. Okay. Remember, Illinois has so many Walmart sites. 1 month actually could be a very many transactions. And that's the reason you can see the data consolidation means I click the button, I want to see Michigan versus Illinois. Okay. You are not going to click the button to really mobilize millions of things adding together. You assume they already done beforehand somehow. So that means you need aggregation, you need to clean the data, you need to do pre-processing. All this processing done. When the people click the button, the summary is there. Right? So that's the reason we were dealing with a very different system. In the next lecture, Dr. Meng Jiang is going to give you details how to design warehouse. Okay, what are the tricks? Okay, thank you.